Okay, so previously we have discussed uh, complete solution is equals to CF plus PI. For CF, we have seen that is this is called function particular integral. Okay. Now there we have seen rules, several rules. Or we can say type. Sixth one was generalized one in function of x. And for complementary function, we have seen that we need to use the d notation ddx, and in place of d we substitute em, and then we will find the values of f. Yes, if f of d of y equals to x, the given OD, then we have substituted, put m equals, put d equals to m in f of d equals to 0, and solve for m1, m2, mn. If we get these values, all are distinct, then we have seen these m's can be real, distinct, real and distinct. This can be real and repeated. Other case we have seen complex. So these are the major three distinctions. Okay. Now we will today discuss the method is called. For example, if the given differential equation is of this form, this is a n y equals to x. So the right hand side should be function of x, and these are constant coefficients. So we can rewrite this case to make it in the standard form. Txn plus Again, the right hand side, it remains the function of x. Okay. So the method of variation of parameter, the method today we will be discussing it. We'll take one small example. For example, d2y dx2 plus b dy dx plus c into y equals to x. So standard form for method of variation parameter. Because we have seen if something is there with this quantity, then we can divide it and we can only think of only two constants, two arbitrary constants. So a standard form or the method of variation of parameter. Okay. Now the working rule for this method is actually first we need to find complementary function as f equals to c1 into y1 plus c2 into y2 and define the particular integral as pi equals to u into y1 plus v into y2, where u and v are unknown parameters. In fact, this can be treated as step 3. Because if we don't check that y1 and y2 are independent, then we cannot proceed. S2 can be treated as find one determinant whose name is Wronskian. It's very important to check, and it is denoted and defined by of this form y1 and y2. This particular function, this Wronskian, this concept is actually useful to verify whether two functions, whether two function y1 and y2 are two functions, and you take their derivative, the determinant is found of this form. Find the Wronskian if, okay, it can be 0, it can be non-zero. If it is 0, then implies y1 and y2 are dependent functions. Remember the linear dependent of vectors? There we have seen that linear combination and then all the coefficients are 0. But here we will use for to verify given two functions are independent or not. So for that we use the concept of Wronskian. And then if this is non-zero, then y1 and y2 are independent. In fact, if we have independent functions, then only we can apply these functions. So that is one disadvantage of this method, variation of parameter. But yet again, and then we will find out step 4 is actually because Wronskian must be non-zero. Otherwise, it will be something by zero. It becomes undefined or infinity. So that is why we must have this is non-zero. So this is one disadvantage of the method. But it is very useful and it can give you the solution without applying all those formulas. That is a step 1 to rule type 1, type 2, 3, 4 and 6. So there sometimes these are not so friendly, or they may be sometimes be difficult to implement. So in that case, if you get this type of uh, approach, these two parameters, unknown parameters, if you can find using this formula, then you will get this is your particular integral and this is your complementary function. So you can see that with the help of complementary functions, we can get the pi. So that will be our actually approach. Now to understand how this formula is valid, that we have to understand that how this is coming. So assume we rewrite the notation equals to x. So let us call it 1. For CF, y double dash plus by dash plus c y equals to 0. Because for finding the CF, we need to the right hand side should be 0. Let us call it 2. Then the complete solution. Then complete solution of equation 2 is actually here CS equals to CF. Let you remember that when that complete solution is actually written as in terms of y. CS y equals to CF plus PI. But for equation 2, the right hand side is 0. So we don't have this PI. So that is why let us write that y equals to C1 into y1, and the general solution or the complete solution for this function is y equals to C1 y1 plus C2 y2. Because if you remember, we have seen that C1 into e power x m1 x plus C2 into e power m2x and so on. So we are calling it y1 and this is y2. And at the very beginning of this ordinary differential equation course, this topic, we have mentioned that if you take this y1 and y2 are two solutions of this differential equation, then we can see that they will satisfy together also. Y1 plus y2 will also satisfy this equation. Sorry, this equation. So we are taking this one. Let us call it 3, and here C1 and C2 are arbitrary constants. So these two are arbitrary constants. So now we have to find out the pi. Let y equals to u y1 plus v y2 with a particular solution. Okay. Then if you differentiate with respect to x, so we get where u and v are unknown parameters. So if you differentiate with respect to x, then we will get this y prime, this is y dash into equals to u into y1 dash plus we will have v into y2 dash plus u dash y1 plus v dash y1 y2. We need to okay. We want this portion y dash u dash equals to 0. So for that we will again satisfying this is u dash y1 plus v dash y2 equals to 0. So we'll see how this is coming. But if for suppose this part is 0, then this y dash will become assume we are telling this because these two unknown variables are there, so we need two equations we will be needed to find out the values of. So from here we will get y dash equals to u y1 dash plus v y2 dash. Now again if you differentiate with respect to x, then we will get y double dash equals to u dash y1 dash plus u into y2 y1 double dash plus v dash y2 dash plus v into y2 double dash. Now if you substitute these values in the values, y, y dashed, and y double prime in the equation 1, and simplify. Then you will get these equations. So y double dashed, y dashed, and y. So the right hand side is actually x. So because of that, if you substitute these values, this is for y double dashed, this one for y dash, and then this is for y. If you substitute them and then simplify, take u and v together. Take u outside and then take all the comments. Now you can see that this is nothing but we are getting the equation, the ordinary differential equation. From equation 2, we can see that this is 0. Again, this is 0. So y1 and y2 are solutions of equation 2 because so this is since y1 and y2 are solutions of equation 2. Equation 2 was the right hand side was 0. So complementary function. So we get these two equations and this is 0. We'll make them 0 so that we can find this one as x. Okay, this portion will become so. So let us call it 5. Now we will take this 4 and 5. 4 and 5 together. We have in this case u dash equals to. Let us write as a division of two determinant. If you see, it is like the Cramer's rule. If you use the Cramer's rule, then you get this value, and if you differentiate, if you integrate it, then you will get this value. Similarly, you get this v equals to this form. Okay. So the particular integral, once you find the particular integral, you can add this to this complementary function, and then you will get the complete solution. So one example will be, so this is one actually important theorem. If px and qx are continuous functions on this particular interval I, then the solutions y1 and y2 of equation 1, that is we have mentioned, are linearly independent in this interval if and only if the Wronskian, that is this determinant, are linearly dependent. If it's 0 for some x0, if there is one x1 on that interval for which that is non-zero, then y1 and y2 are linearly independent. Now, for example, you can see that if you take y1 equals to this and y2 equals to this one, then the Wronskian will be -2, which is non-zero. So, for any value of x, this y2, y1 and y2 are linearly independent. Now, if we have a third order differential equation, then the Wronskian will be of 3 by 3 order. So in that case, we will have y1, this is y1 dashed, y1 double dashed. So first order, second order derivatives will be included in the Wronskian. Now if you try to solve this problem, then it will become, so first task is to make it 0. Okay, so if you write it in terms of f of t of y equals to x, so here it will be d2 plus 1 of y equals to cosec x. Okay, now the auxiliary equation is m square plus 1 equals to 0. So from here m equals to plus minus I. Now the complementary function is a cosine x. So that means if you write it in terms of 0 plus minus I, so e to the power, actually the formula was e to the power 0x into a cosine x plus b sine x. So this is nothing but it will be 1 and then a into cosec x, cos x plus b into sin x. So if you can write it as y1, and if you write it as y2, then you can get let y1 equals to cos x and y2 equals to sine of. Then our claim is pi equals to u into y1 plus b into y2. But remember, we need to find out the Wronskian. Before that, we cannot proceed. So this Wronskian y1 and y2. This is y1, y2, y1 prime, y2 prime. This is cosine x. This is sin x. So derivative of cos x. So this is minus sin x. Derivative of sin x. This is cos x. So if you expand this, if you evaluate this determinant, then you will get cos x square plus sin square x. So this is 1, which is non-zero. Okay, now you can claim that pi will be u into y1 plus b into y2, where y1 you have seen cos x, y2 is sin x. U will be found out by minus of x, sorry, not x, this is minus y2 into x. X is the right hand side, and then here Wronskian of y1 and y2 into dx, and v will be found by this integration y1 into x by Wronskian y1 y2 into dx. Remember, Wronskian, if it is 0, then this formula is not actually applicable. So that is why we need them non-zero. So this verification is important. Okay. Now we can go through it. So u equals to, already we have seen this is 1. So y2x into dx. And this x is, if you remember, f of d into y equals to x. So that is our given equation. Here in this case, x is cosec x here. And v equals to y1 x into dx. Since Wronskian y1 and y2 equals to 1. So let us calculate this u. This is negative. y2 means sin x. y2 means sin x. And then x is cosec x into dx. So this is what? Minus 1 dx, which is nothing but minus x. For particular integral, we do not use any constants because we have assumed already two arbitrary constant here. And for a differential equation of order 2 will contain only two arbitrary constants. Now, if you try to find out the values of v, so v would be, this is cosine x, and this is cosec x. Into dx. So this is going to be integration x dx. So this is nothing but integration logarithmic of sin x. Now you can write down the solution. So particular integral uy1 plus vy2. Here you get u1 was minus x, and this is cosine x, plus v equals to log sin x, and y2 equals to sin x. So if you just write down one simplification, okay. Hence the complete solution y equals to cf plus pi. Here it is a cosine of x plus b sine x, then plus, this is negative, of x cos x plus sin x into logarithmic of sin x. So that will be our actually final answer, where a and b are arbitrary constants. So that's how you will try to find out the solutions. So for example 2, so this is example 1 I have taken. For example 2, you can find it or verify. I would say verify this solution whether it is correct. For example 3, you try to verify again. And yeah, these are your practice problem. Verify these results whether they are correct. Yeah, that's all for today. If you have any doubt, you can ask me.